Hello. We learned this interesting example where if you use a single year data, then your coefficient was positive, but when you take the difference, your coefficient becomes negative. And the reason was because of the omitted variable bias. Especially the omitted variables are time constant, does not change over time. So, it's my graph. I like this graph a lot. So it's my graph. Suppose that there are two states like this, and x is here, y is here. If you ignore the panel structure, suppose that you do not observe what is blue and what is red, then the data looks like a nice increasing pattern, has a nice increasing pattern. But if you think about the colors, so red has this color, this, and blue has this. So if you split them, it has different coefficients. So this regression utilizes the color as an information. So using this color and using this color, but this regression does not use the color as an information. So like uh, utilizing the panel data structure changes your result a lot. Okay, so isn't it nice? I like this graph. I drew this, and I think I'm very proud of myself drawing this graph. So now we are going to consider how we can implement that, or in a general setup, how we can set up a general model for this idea. Here is the model we have in mind. So suppose that we have more than two time periods with zi. So remember, zi, we introduced the omitted variable zi, but it is not observed. Just we have this here because we have to consider this. Otherwise, we suffer from the bias. But the problem is we have to remove this. We have to get rid of this by some method. So that method is called the fixed effects regression model. Fixed effects, the name is fixed effects because the effect, say there is an effect that is specific to, say, Tesla or New York State or specific to California. So it is fixed, it does not change over time, and it is specific to an individual or a state. So why it's named as fixed effects. And we'll see. And in our example, just to describe this method, we will consider three states: California, Texas, Massachusetts. Let's replace Massachusetts with New York. Massachusetts is too long to say. Say New York. Anyhow, so then there are three I's. I is a state, so I may be California, I may be Texas, or New York. And the Z is different. California and Texas and New York have different attitude toward drinking, and also different quality of road and different traffic density. We don't observe them, but that's just our examples, the examples for these omitted variables. And then what we have here is for California, you may write it this way: intercept and beta 1 times beer tax plus beta 2 times omitted variables, time constant omitted variables. And we are going to bundle the intercept and this omitted variable because both do not change over time. So these two guys, so y depends on t, x depends on t, u depends on t. But only these two terms do not depend on t, so we will bundle them into alpha. So alpha is defined as beta 0 plus beta 2 z California. So alpha is just all the terms that do not change over time. And also you may interpret alpha as an intercept, but it is an intercept specifically for California because different states, New York would have different value of z, so this part will be different. This part will be different. So New York's alpha would be different. So this is an intercept, but it is specific for specific to California. Beta 1 is the same. The other guys are the same. So what you need to understand here is you may treat the omitted variable, which is time constant, as individual or state specific intercept. This is an intercept only specific to this observational unit, cross-sectional unit, right? All the other slopes are the same across states. That means, say, Texas has this form. Texas has its own intercept, which may be different from California. And say Massachusetts, Massachusetts has its own intercept. So different states have different intercepts. However, beta 1 is the same. Of course, tax rate may be different. Beer tax may be different, but it has to be different. Beer tax has to be different to compare across states. Then, this is what we observe in the data. So X is beer tax, or like say, like in this case, I cannot say it is a beer tax because the graph is increasing, the slope is increasing. So, like anyhow, suppose that so X is on the X horizontal axis, Y outcome is on the vertical axis, and then Massachusetts starts from here at this slope, and Texas starts from here at the same slope, and California starts from here at the same slope. So the slope are the same, so they are parallel to each other, but their intercept may be different. So for some reason that we do not observe in the data, California has a higher outcome than the other two states. I don't know why, but we can guess as we did, like say, California may have different culture, may have different density. So you can think about some different factors, but they are not observed. So for unobserved variables, California has just a higher outcome, but Massachusetts has lower outcome due to unobserved reasons. So this is exactly the same idea what we did in the earlier example. And then you may consider this in this way. So that means the intercept should be changed across state. So it is equivalent to include state dummy variable. Say DCA takes 1 only if the state is California, and DTX takes 1 only if the state is Texas. So then the dummy variables, because there are only three states, we have to leave out one state, here in this case Massachusetts. So then beta 0 is the intercept for Massachusetts because Massachusetts have 0 and 0. And for California, the intercept is beta 0 plus gamma California. This equals to 0, but this equals to 1. So beta plus gamma California is the intercept for California. And for Texas, this is 0 and this is 1. So the intercept is beta 0 plus gamma TX. So by including the dummy variables, you can capture the difference in the intercept. So this model is a dummy variable model, or it is equivalent to write the equation this way. So it's just a matter of how you define the variables, how you write the equations. So the idea is they have the same slope parallel lines, but the intercepts are different. And the difference in the intercept is coming from the omitted variables. You don't observe, but they are time constant. So because of them, you have difference in the intercepts. So far, we learned two different approaches. Basically, they are the same models, but you may consider in two different ways. In general, fixed effects model is more common. So, like anyhow, they are equivalent. So I'm going to call this fixed effects model. Okay. And then how do we estimate? So far, actually, we considered three different models. First, in the example, we considered changes approach, like say calculating the differences and calculating the changes. That was one possible way, and another approach is using dummy variables n-1 binary dummy variables method. And number two is entity demeaned. I'm going to explain these three methods. They are in the end equivalent. They should be equivalent. They are the same methods resulting in the same results. So I will just explain why they are equivalent just intuitively. I'm not going in details about their algebraic properties. So I think I will stop here and we'll continue the estimation methods in the next lecture. Thank you for watching this and have a nice day. Bye.